Okay, so today we're going to look at 6.6, which is looking at inverse trigonometric functions for our 6 different trig functions. So anytime we want to represent an inverse trig function, we denote it using a little exponent of -1. So it'd be like sine -1x is actually the inverse sine of x, or it's also written as the arc sine of x. And that goes for all of the 6 different trig functions. So the inverse cosine function is also known as the arc cosine function. Inverse tangent is the arc tangent function. Inverse cosecant is the arc cosecant function. Inverse secant is arc secant. And inverse cotangent is arc cotangent. Okay, and then because these are inverse functions of our trig functions, when we combine them, our inverse functions and our regular functions, they will cancel out. So the inverse sine of x just cancels the inverse and the sine, and you're left with just x. The same thing goes for the inverse cosine of cosine of x equals x, inverse tangent of tangent of x equals x, inverse cosecant of cosecant of x equals x, inverse secant of secant of x equals x, and inverse cotangent of cotangent of x equals x. Okay, so we're going to look at evaluating some inverse functions first. So if I look at example 1a, I'm given the inverse sine of 1/2, and I'm asked to figure out what that equals. And so I'm going to set that equal to some variable x in order to figure out what that x value is. And in order to get rid of an inverse sine function, I'm going to take the sine of each side. That way my inverse sine and my sine cancel. And so I'm left with 1/2 equals sine of x. And that is useful because we can find sine of x on our unit circle. So
sine is y, right?
Sine is y. So if I'm looking to figure out where my sine function equals 1/2, I can see that my sine function equals 1/2 here at pi over 6 and here at 5 pi over 6. And since I only care about, you really only care about the positive side of your graph here, from negative pi over 2 to pi over 2, I'm going to just use pi over 6 as my value. So that tells me that x is equal to pi over 6. Okay, so let's look then at part B, tangent of the arc sine of 1/3. First thing I'm going to figure out is the inside the arc sine of 1/3. And the arc sine of 1/3 can be rewritten the inverse sine of 1/3. And since I want to figure out what that equals, I'm going to set that equals to some unknown variable x. In order to get rid of my inverse sine, I'm going to take the sine of each side so that my sines cancel. So I'm left with 1/3 equals sine of x. Okay, and so this is a case if you look at all of your different y values where you aren't ever going to find 1/3 specifically on your unit circle. So that's the case where our calculator is going to come in handy. So if you pull out your graphing calculator, your inverse sine is a function on your graphing calculator that you can use. Okay, and so in order to be specific, let's make sure that our mode is actually in degree mode because radian mode would have us dealing with pies, and we don't want to deal with pies. Okay, so if your calculator is not in degree mode, make sure you change it under mode. And then right above your sine, if you go to second sine, it will give you inverse sine. And so since I'm trying to find the inverse sine of 1/3, I'll start with that, and that gives me approximately 19.47 degrees. So x is approximately 19.47 degrees, since I'm in degree mode. And then the second part of that was finding the tangent of that arc sine. So I'm going to find the tangent of that 19.47 degrees. And since 19.47 degrees isn't on your unit circle because it's not an even percentage, then we'll just go back to our graphing calculator and do tangent of 19.47. And that gives me a value of approximately 0.354. So the tangent of the arc sine of 1/3 is approximately 0.354. Okay, so use your unit circle to be exact. If it's not on your unit circle, use your graphing calculator, and that will give you the second value. Second part of what we're going to look at today is derivatives of inverse trig functions. Okay, so the derivative of the inverse sine function is 1 over the square root of 1 minus x squared. The derivative of your inverse cosine function is -1 over the square root of 1 minus x squared. So sine and cosine are the same, except the cosine is negative. The derivative of your inverse tangent function is 1 over 1 plus x squared. The derivative of your inverse cosecant function is negative 1 over x times the square root of x squared minus 1. The derivative of your inverse secant function is 1 over x times the square root of x squared minus 1. And lastly, the derivative of your cotangent function is negative 1 over 1 plus x squared. Okay, so if I look at example 2, I'm given the function f of x equals the inverse sine of x squared minus 1. I'm asked to find the domain of f prime of x, and the domain of f prime of x. Okay, so domain refers to your eligible x values of your graph, the x values of your graph that your graph touches. So if I look at the inverse sine function of x squared, I'm going to graph that and see what my x values are. Inverse sine of 1 minus x squared. Okay, so to get your inverse sine function, it's x squared minus 1. You use your second sine function. And since we're doing x squared minus 1, we'll do the inverse sine of x squared minus 1. And you're going to graph it. And I don't like that graph. So let's change our mode back to radian and see if we get a prettier graph in radian mode. Much prettier. Okay, so if I want to find my x values, I'm going to kind of trace my graph to see if I can figure out approximately what that endpoint is on each side. And so it looks like my y values disappear if I go any further to the left of about negative 1.363 or 1.364 if we round it. So I know that my first value is negative 1.364 is going to be less than or equal to my x value, and now I need to find my right endpoint. So I go on my graph and I keep tracing in the other direction. Until I run out of y values, I get to approximately positive 1.364. So my other value then would be positive 1.364. The second part of what it asks me is to find the derivative of f prime of x. So let's start with what's the derivative of the inverse sine function? What was my formula for that? So my derivative of just the inverse sine function is 1 over the square root of 1 minus x squared. So I'm going to start by using that, but since I have more than just an x on the inside, I'm going to need to use my chain rule. So I'm going to take the derivative of the outside times the derivative of the inside. So the derivative of my outside then, if my derivative of inverse sine is 1 over the square root of 1 minus, in this case my inside is x squared minus 1. So 1 minus x squared minus 1 squared. Times the derivative of my inside. So what is the derivative of an x squared minus 1? If I ignore the sign, 2x. So the derivative of x squared minus 1 is 2x, so times 2x. And then if I keep trying to simplify that, 1 times 2x just gives me 2x, so I know I have 2x on top. If I square the bottom, I get x to the 4th minus 2x squared plus 1. So I get 1 minus the square root of x to the 4th minus 2x squared. Which then my 1 minus my 1 cancels. So I'm left with negative x to the 4th plus 2x squared on the bottom. And then I can cancel out an x from each of these things. So I'm just left with x. So I'm left with x cubed. So I'm left with 2 over negative x cubed plus 2x. That's it. Okay, and that asks us to find the domain of f inverse of x. So now we're going to graph 2 over negative x cubed plus 2x and figure out what we get for that. Pretty. Okay. So I can see that my graph goes on forever and ever and ever and to the left. See that it goes on forever and ever and ever to the right. My only question is right here, I have a vertical asymptote at x equals 0, and so I can see that my graph does not ever cross x equals 0. In fact, it stops and stops. So that tells me that my domain is from negative infinity to positive infinity, except that x cannot equal what value? Where was my vertical asymptote at? 0. So x cannot equal 0. So x can be any value from negative infinity to infinity except for 0. Okay, let's do one more. So example 5 asks us to differentiate y equals 1 over the inverse sine of x. Okay, and we know that our derivative of inverse sine of x was what, Mikey? Okay, so I know that my derivative of inverse sine of x is 1 over the square root of 1 minus x squared. But this is 1 over inverse sine of x. So I'm going to rewrite this as the inverse sine of x to the negative 1 power. Because I'm going to move it up so we don't have a fraction. So what that tells me to do then is, if I continue to apply my chain rule, I take the derivative of the outside times the derivative of the inside. So in this case, my outside is this negative 1. So if I were to derive that, I roll the negative 1 down. The inverse sine of x stays the same. And then I increase this negative 1 to make it negative 2. Times the derivative of the inside, which is just the derivative of the inverse sine of x, which Mikey told us was 1 over the square root of 1 minus x squared. Now we can simplify. This negative 2 can become a positive 2 if we move this inverse sine of x down to the bottom. So the inverse sine of x squared. The negative 1 would stay on top. And I'm taking that times 1 over 1 minus the square root of x squared. And then if I just multiply my fractions straight across, negative 1 times 1 is negative 1. the inverse sine of x squared times the square root of 1 minus x squared. Can't simplify that any further. And then the second part of that asks us to find the derivative of x arctangent of the square root of x. So I'm going to rewrite this arctangent as the inverse tangent of the square root of x. Write that here, more space. And then, Mark, what's the formula for the inverse derivative of the inverse tangent of x?
1 over x plus 1 over 1 plus x squared.
Okay, so the derivative of my inverse tangent of function is 1 over 1 plus x squared. And so using that formula, then I'm going to start to differentiate this. Because these are two separate functions, then I'm going to take the derivative of the first times the second plus the derivative of the second times the first. So what's the derivative of x? 1. Okay, so the derivative of x is 1. So the derivative of the first times the second. And in this case, my second is just the inverse tangent of the square root of x. That stays the same. Bless you. Plus the derivative of my second, and we just said the derivative of the inverse tangent is 1 over 1 plus x squared, but in this case we're dealing with the square root of x squared. And because this is kind of like its own inside function, we have to differentiate that. Square root of x squared is just the same thing as x to the negative 1. And so the derivative of that, if I roll down my 1/2, x becomes 1/2 x to the negative 1/2. Okay, so I did the derivative of my second times my, times my first, so times x, because I still have to take times this function. Okay, so the first part, really simple, second part, really messy, right? Because the derivative of x is just 1, so that was easy. Okay, so 1 times inverse tangent of x is just inverse tangent of the square root of x. For the second part, we need to start simplifying. So the square root of x squared cancels. So I'm given 1 over 1 plus x times, if I want to make this be simple, I would need to turn it into a fraction and rewrite my fractional exponent as a root. So this was x to the negative 1/2 is the same thing as 1 over the square root of x. So simplifying that, I get times 1 over 2 square root of x. And then I still have times x at the back. Okay, so continuing to simplify, the first part stays the same. Now let's just multiply all of our fractions straight across. So 1 times 1 times x gives me just an x. If I look at the bottom part, 1 plus x times 2 square root of x, if I pull that 2 out front and leave the square root of x back, times 1 just gives me 2 times 1 plus x times the square root of x. So that would be my giant derivative for x, arc tangent square root of x. So it's a lot of different things combined that we've learned, but it's fun because it's trig. So 459, 1 through 10, 12 through 14, and 23 through 24. We're going to work on this today and tomorrow.